Hi folks, so let's pick up where we left off talking about stepper motors. Last time we were talking about stepper motor design. This time we want to talk about stepper motor operation. So when we're driving a stepper motor, remember that we're going to be giving digital pulses, and so we can do what's called full stepping, which is rotating one full step at a time, using either one phase at a time, a one phase on sort of situation, or two phases at a time. And what I mean by one phases or two phases is that on the left you can see what we'd call one phase, and in that case the A phase is on while the B phase is off, or the A phase is reversed while the B phase is off, or the B phase is on while the A phase is off. You can see only one of them is activated at a time, whichever direction it's going. On the right we have the two phase on case, where you can see in the first chunk there, time A, both A and B are active at the same time, versus in C they're active and they're reversed at the same time. Neither phase is turned off, they just on forwards or reversed. So one phase on at a time is sometimes called wave drive, and two phases on is sometimes called full stepping. Now if you squint your eyes, you can see that if we continued this pattern, it would look vaguely sinusoidal. It's not super sinusoidal, but it looks kind of vaguely sinusoidal. So let's look at that one phase on case. So in this case, on the right there, you can see that I've got a hybrid stepper motor. It's got the variable reluctance characteristic of having that iron core, and it also has the permanent magnet stuck on around that iron core. And then we've got phases A and B. A is going to be the vertical components there, and B is going to be the horizontal components. And of course, in a real stepper motor, we'd have many more phases, or many more sets of electromagnets around the outside, even if we only had two phases. But we would have more of them there, and in this case, we're just looking at a simplified example. So in the A chunk of time, that's confusing, lowercase a chunk of time, phase capital A is on, phase B is off, and so as we go to chunk of time lowercase b, we turn off A and we turn on B. So in this case you can see that now B is the horizontal phase there is active and the vertical is off, and we've rotated our rotor. And we'll reverse A now and turn off B, and we'll reverse B and turn off A. And as we rotate through, you can see we've got an alignment mark. We've rotated 90 degrees, and it's taken us 4 steps to do it. So this is about 22.5 degrees per step. And that's how you would refer to a motor. They are typically classified in terms of the number of degrees per step. Now, in this case, the torque that is being generated to rotate the motor is coming from a single phase interacting with the rotor. Compare that to the two-phase on case, where in this case we've got A and B both activated at the same time. So we get this initial little misalignment relative to what we had in the last case. And that misalignment, it's not really a misalignment, it's just the rotation that is going to minimize the overall reluctance, which you might remember is the magnetic equivalent of resistance. And so this slight misalignment is going to cause that reluctance to be minimized when you consider both the path through from A from the top down to the bottom, as well as B from the left to the right. So as we change our phases here, we will reverse A first and keep B active, and so we rotate a little bit. We'll reverse B and keep A reversed, and then we will bring A back to the original direction and keep B reversed. And so you can see that we've rotated through 90 degrees again. So there's no difference here. One phase on, two phases on, full stepping is still the 22.5 degrees per step. It is still one full step. Now in this case though, the torque is coming from both phases active at the same time, so you would naturally assume that the two-phase on case is going to generate a larger torque. So then, how are we actually wiring a real motor? Well, when we're wiring a real motor, we can wire it in what's called unipolar or bipolar wiring. Unipolar wiring means that I am going to reverse the current direction for the phases by having actually two wires there, and each one of them only goes a single direction, so I'm doubling up the wire. Whereas bipolar, I'm actually going to reverse the direction of the current through the winding, which you may remember from talking about DC motors means that I'm going to need an H-bridge. How do I do that with the unipolar? Well, it's called bifilar winding. So as you can see in the picture on the right with this toroid here, I've got a pair of wires that are parallel, and I have wound both of them around the outside of this toroid, and on the left you can see another example of that. But these two wires being next to each other means that if I want to go, if I want the phase of the electromagnet to go one way, I run the current in one direction through in this case the red wire, let's say, and if I wanted to go the other way, I'll run the current the other way through the gold wire and turn off the current through the red wire. And so this sort of scheme was developed for unipolar motors, but you can also apply it to bipolar motors to get yourself some additional flexibility. So something like this. I might have 4 or 5 or 6 or even 8 leads coming off of a stepper motor. Now 4 leads means that I've only got 2 leads on each of my phases, which means it has to be bipolar driven, which means it can't be bifilar winding. But if I've got 5 or 6 or 8 leads, that means that I could have bifilar winding. And if I've got bifilar winding, then I can do some fun things. So for instance, on the 6 lead, then you see that I could drive it using only the outer leads on each of those, and I could treat it just like the 4 lead. Or I could use that center tap, and I could treat this as a unipolar drive. And the same thing for the 8 lead. I could tie those two centers together and make it a center tap just like the 6 lead, or I could treat them independently. It gives me a lot of flexibility. So here's some different configurations that you can use. You can see that the 8 lead there, I can run it in unipolar, I can run it in bipolar series, I can run it in bipolar parallel. There's lots of different ways you can do this. Just kind of depends on what you're doing. So with that in mind, if I've got unipolar or bipolar, then I'm going to be activating this either with transistors for the unipolar, because I'm only controlling the current flow in one direction, or an H-bridge, like you see on the right, for bipolar, because I need to control the direction of the current either one way or the other way. And so I suppose I should have pointed out, these are intended to be a side view of a motor, so that small shaft sticking out, that's the rotor for the motor, and the larger block is the body of the motor. Hopefully that wasn't confusing. So if I go through my step pattern then, for unipolar and bipolar, on the left here we've got a bipolar step pattern, and above it the bipolar motor, and on the right we've got 2 different schemes for the unipolar. I'm going to go ahead and draw in that this is going to be my voltage supply, this is going to be my voltage supply, and then what I'm going to do with Q1 through Q4 is I'm going to control the connection to ground, which will allow the current to flow. So starting with the bipolar case there, you can see that if I were to activate Q1 and Q4, also Q5 and Q8, and deactivate Q2, Q3, Q6, and Q7, then the effect is that I'm going to have current flowing both through A and B phases, and it's both going to be what we'll call positive. I mean, the sign convention here is up for grabs, but I'm going to assume that that's going to be positive. Excuse me. So now I'm going to reverse the Q5, Q8, Q6, Q7 pairs. Well, that's going to reverse the direction of the current through the B phase. Then I will reverse the Q1, Q4, Q2, and Q3. Well, that's going to reverse the current through the A phase. And finally, I'm going to reverse the current through the B phase again. And you can see that this is my full stepping 2-phase on case. I'll get back to the first one there. Now, we could also do something that's called half stepping. And in half stepping, well, I'm going to turn on the A phase to start with, and I'm going to turn on the B phase for part of it, and then turn off the B phase for part of it. And so I'll reverse the B phase, and now the A phase is going to stay on, and then it's going to turn off, and then it's going to reverse. So you can see that now I'm mixing my 2-phase on and my 1-phase on full stepping, and the effect is going to be a half step or 8-step sequence. So instead of a full step, previously we had 22.5 degrees per step, now I'm going to get half of that in my half step sequence. Now, we look at this and we could build our own motor drivers, but of course I'll show you in a couple of slides. We wouldn't actually build an H-bridge for each of these. What we would do is we'd buy an off-the-shelf motor driver, typically. Unless you have something special, then you might need to build your own. So let's look at the phases here. In this case, I've got the two-phase on. I'm going to control the phases. If I'm going to do, with the two-phase on, remember I'm going to do bipolar, and I'm going to control them with the the H-bridge. And the bottom I'm doing with the unipolar, which means I'm going to control the individual transistors. And if I'm looking at the individual transistors, then you can clearly see that Q1 is the inverse of Q2, and Q3 is the inverse of Q4. Now the other thing that you might see here is something called a phase diagram. So in a phase diagram, I might look at I1 and I2, the current through phase 1, the current through phase 2. And in this case, you can see that my first time interval, they're both positive. We'll call that 1. My second interval, 1 is positive and 2 is negative. My third interval, they're both negative. And my fourth interval. So you get a phase diagram that looks something like that. Now, if I'm looking at these, whether I'm looking at an H-bridge or I'm looking at the transistors, I should be able to come up with a way to trigger these, because these are, again, just digital signals. And these are digital signals that are responding to my desire to rotate by a step. So I am issuing a command to whatever is driving this to say, I want to rotate a step now. You come up with a way to drive the transistors or to drive the H-bridge. Well, we should be able to come up with a way to do that. Essentially, we're saying that there's this black box that's going to accept inputs of a pulse and a direction. Which way do I want to rotate and when do I want to do it? And should give me outputs. In this case, I've written them for the transistors, Q1 through Q4, that will give me my appropriate pulse pattern for the transistors that will rotate the motor. Well, we know that we only need two outputs because, again, Q2 is the inverse of Q1, Q4 is the inverse of Q3, so I will choose only two outputs, Q1 and Q3. Those are my unique ones. And again, my inputs are going to be the pulse and the direction. How can we do this? Well, an easy way to do it is a finite state machine. With a finite state machine, I've got 4 states, because I've got 4 distinct steps here, and my 4 states are going to be defined here by my outputs. My outputs are unique in this case, which is convenient. So in the first one, my outputs are both high, and in the second one, my output are 1, 0. The phase 1 is high, the Q1 is high, the Q3 is low, and I get there by asking it to go what I'll arbitrarily call the positive direction, and a pulse is true, so I've asked for it to step. So anytime I ask for it to step in this direction, it's just going to follow through that sequence. And if I ask for a pulse the other direction, well, it's going to go the other way. So this is just a finite state machine for full stepping. Pretty easy. So that's full stepping, and I mentioned that there's also something called half stepping. So half stepping says that if I turn off the coil instead of fully reversing it, and do that in this intermediate step, then what I can end up with is halfway between these positions. Now, the downside of that is anytime you're turning off the current, you know from looking at the one-phase on versus the two-phase on case that you're reducing not just the current, but you're reducing the torque. So you might need to actually increase the other phases current so that you increase the overall torque. And so if you start looking at these phases and you look at the current through them, well, now they start to look really sinusoidal. And not just really sinusoidal, but they look really sinusoidal and 90 degrees out of phase, so they start to look like what we would call quadrature. And then obviously you can take it one more step from there, is that these are sort of roughly sinusoidal. What if I got them really sinusoidal? Well, if I get them really sinusoidal, then I'm going to get smaller steps. And so if I get these sinusoidal signals and I start getting them the steps really small, then we get what might be called microstepping. So in this case, you're gonna get away from the digital nature of the motor, and you're going to start approaching more of a continuous analog nature. And now you need a different kind of amplifier because it's not purely digital anymore. Now you need a proportional amplifier in order to do the current. So is it better? Well, maybe. Personally, I find that half stepping and quarter stepping are about all I need. It depends on what kind of accuracy you need. So in order to get full stepping, quarter stepping, even eighth stepping, I'll just buy an off-the-shelf motor driver. So for instance, this is the one I happen to have in the lab, but there are certainly other options. Here's a $15 stepper motor driver that will drive a 4, 6, or 8 wire stepper motor with full, half, quarter, or eighth stepping. And you can see that's a relatively cheap product, and it implements something akin to the state machine that we were just seeing. So that's kind of the construction and how you would drive them. But then there's also some characteristics you need to keep in mind. So when we are doing a step, this chunk of mass is going to rotate. And just like any other chunk of mass that rotates, you have to worry about the damping. Well, in this case, there's a spring action from the magnetic field, but there's really not a lot of damping in there. And so as it rotates, what you expect to see is that it's going to tend to overshoot and then oscillate as it settles down. This is just an underdamped second-order system. Well, as you know, with an underdamped second-order system, it has what we call a resonance frequency, and so you really need to avoid that resonance frequency. But what is the resonance frequency? Well, a permanent magnet stepper is typically going to rotate somewhere between like 7.5 to 15 degrees per sep. A hybrid is going to be a little more accurate at 0.9 to 3.6 per sep. But what you're looking at is somewhere on the order of 70 to 120 steps per second. So 70 to 120 steps per second. So that's essentially the limit on your pulses before you hit what we will say is a resonance. So if you get close to that resonance, you're going to start to see that the steps are not going to be accurate anymore. You're going to start to see that oscillation means that you're going to hit desynchronizing or a stall or just really weird behavior. So I've included a video link. I found this YouTube video that shows a stepper motor near its resonance. It's still going around in the circle like it's expected to do, but now it's bouncing all over the place and it's not accurate. So remember that one of the big things about a stepper motor is that we like them for feed-forward sensorless control. If we are now stepping close to the resonance and we are no longer accurate, then the feed-forward nature of it is going to cause a problem because we don't know that we're not accurate. So you really have to know what the resonance frequency is for your motor and don't get close. So don't step near the resonance. So if you can, you could switch between full and half stepping. You could add damping if you need to, but don't get close to the resonance. Another characteristic that is useful to know is the holding torque. So when the stepper motor is sitting there at idle, you still got current going through those coils, unless you're using a permanent magnet and you're relying only on the detent torque. But you still probably got current going through your motor, so it's sitting there holding its position. So how much torque can you apply before you overwhelm that and it slips? Well, you can test it if you need to, or you can just read the spec sheet. But we consider that to be the holding torque. And when your permanent magnet stepper slips, it's going to slip not one step, but 4 steps. And so if you are relying on this thing with no feedback, which is generally what you would want, because that's the point of this, and you've got some sort of load that's going to be causing a problem in terms of torque, then you need to know what that load is going to be so that you don't exceed the holding torque of your stepper motor. If you do and you lose your position, well, again, there's no sensor, so it's lost. Without that position, then all of the accuracy of your system is lost, which is a bad thing. Now, you could also talk about the running torque, and the running torque is the maximum torque before you start to skip steps. So if we think about our holding torque, we think about our running torque, we might look at a torque speed curve the same way you would with a DC motor. And so in your torque speed curve, you're going to have this load-dependent curve. And there's a couple of things you need to know. So there's this slew curve on the outside, and there's a start-stop curve on the inside. And so we might say that this region is the start-stop region. Let me write that out, start-stop region. And then this one is our slew region. And so what that means is the start-stop region is the region in which you can, and remember this is a combination of speed and torque, this is the region that you can start or stop the motor instantaneously. If you need to get into the slew region, then you have to start in the start-stop region and then speed up to get there. So you got to worry about your acceleration rates. So we also have our no-speed holding torque. Excuse me. And we have what's sometimes called our max slew rate. That's our maximum speed. So that's your torque speed curve. Again, it's load dependent, and it tells you about the motor characteristics. So finally, when you're driving one of these motors, you need to worry about temperature. So I've said it a couple times, but even when you're stopped, because you've got that holding torque, you're going to be driving current through these windings, which means you're still going to be generating heat, even if you're sitting still and not doing anything. So some motor drivers have an idle setting that you can trigger, and that idle setting is going to reduce the current through the coils, which means you're going to get consequently less torque. But if you know that your lower torque, holding torque is still good enough, that's great. So you need to watch out for the temperature. The temperature is based on the thermal breakdown for the insulation. So what happens is that if you exceed the temperature limits, things are going to start melting, and then it's going to be damaged, and that's a bad thing. So if you're really worried about the current and you're worried about the temperature, then current mode drivers, where you're controlling the current instead of controlling the voltage, gives you a better read on making sure that you're not overheating things. Also, you're going to see your voltage spikes with a short duration during a transient time when you're reversing current, which makes sense because you've got this inductance and you're having a sharp transition, a step change, so you would expect to see a voltage spike. But that's relatively short, so you shouldn't see a huge temperature increase for that. Mostly, I would worry about just sitting there idle. There's no airflow, so you don't have any cooling typically, so you're just sitting there generating heat and warming up. So as long as you can control the heat and you don't step too fast, stepper motors are great for feed-forward position control. So now you know a little bit about the design and the operation of stepper motors. And next time I think we're going to talk about communication.